we are diving into something that's shaping the way modern systems are built: microservices and API design. These aren't just technical decisions, they are how high performing teams move fast, stay flexible, and build systems that scale without slowing down. Let's get into it. So, imagine being able to ship new features weekly without downtime. Imagine your team deploying changes independently without much conflicts. And imagine an architecture that adapts to traffic spikes instead of crashing under pressure. That's what microservices and smart API design unlock. Systems that move at the speed of your business, not the other way around. Today's users expect fast, seamless, and reliable experiences every time. If your system is slow or fragile, they'll move on in seconds. Microservices break down big, bloated code bases into smaller, agile units that evolve independently. APIs connects those units into something greater than the sum of their parts. Together, they give you a foundation that's not just scalable, but adaptable, resilient, and ready for what's next. So, now let's understand microservice architecture. So, let's start with the basics, like why are microservices such a game changer? Independent services, microservices break down your application into small independent units, each focused on doing one thing really well and at a time. These services are autonomous, and because of that, they are easier to build, test, deploy, and scale. What's powerful here is how this changes the way teams operate. Instead of coordinating across a massive code base, each team owns their own service from start to finish. That means faster decision making, quicker releases, and fewer bottlenecks. Technology diversity. So now imagine you are building a real time recommendation engine for an e commerce site. You might need lightning fast response times. So you build that service in Rust or Go for performance. On the other hand, your order history service, where speed isn't as critical, could be built in Node.js or Python, where development is faster and more flexible. Team autonomy. Each service can use the tools that are best suited for its specific purpose. And the beauty of it is, these choices don't interfere with other parts of your system. You also get pinpoint scalability. If one service is under pressure, you don't need to scale your entire system. Just scale that one service. It's precise, efficient, and cost effective. And deployment becomes a breeze. You are no longer tied to a big bang release where everything ships at once. Services go live when they're ready, which means less risk and faster iteration. Microservices shift our mindset. We stop thinking in terms of projects and start thinking in terms of products. Teams don't just deliver code, they own outcomes. And that's a huge step forward in building better software. Now let's understand what domain-driven design means and build what the business speaks. Alright, so we have decided to build microservices. The next big question is, how do we decide where one service ends and another service begins? So this is where domain-driven design comes in. It's like giving your architecture a map of the business. Start by identifying bounded context. These are self-contained zones of logic where everything makes sense in that word. For example, what the word order means in a sales context might be very different from what it means in a shipping context, right? Each bounded context gets its own vocabulary and rules. Try to establish a unique language. That means everyone, developers, product managers, stakeholders, uses the same terminology. So instead of one person saying basket and another saying checkout payload, everyone just says cart. That alignment avoids misunderstandings and speeds up collaboration. And the next step is to model domain entities. This approach also keeps your services from overlapping or becoming blurry. You won't end up with two services doing this kind of same thing but with slightly different names. And the next step is to define service boundaries. So, why does this matter? You are no longer building from vague requirements, right? You are directly coding the business logic into your services. It's cleaner, more accurate, And when business needs change, your systems adapt faster. Moving on to the implementation strategies. So let's talk about turning your microservices design into something real and fast. Independent deployment. So the key here is independent delivery. Each service should have its own CI/CD pipeline. That means when one team finishes a feature, they don't have to wait for another team or coordinate a big release. They can test it, ship it, and monitor it all on their own timeline. And the next one is data isolation. A key microservices principle is that each service should own its own database or data store. With separate data stores, services stay independent, making it easier to evolve and deploy them without breaking others. And communication patterns, we have to choose wisely here. Use REST or gRPC when the response is immediate and necessary. But for everything else, lean on to GraphQL, Kafka, RabbitMQ. This allows your services to talk without being tightly bound to each other. If one is slow or down, the rest of your system doesn't have to wait. On the deployment side, embrace containerization. So Docker makes your service portable. Kubernetes add orchestration, scaling, and self-healing. It's like giving your architecture superpowers. And here's a big one. Instrument everything. Logs, metrics, traces. You want to know what exactly going on in your services at all times. Observability isn't optional when you've got dozens or hundreds of moving parts. Next, let's look at the resilience patterns, designing for chaos, I would call it as. Let's get real for a second. Things will go wrong, services will fail, network will time out, dependencies will become unreliable. The question isn't if something will break, it's how your system responds when it does. That's where resilience patterns comes in. So these are your safety nets. Let's look at what circuit breaker pattern is. It's like the fuse box in your house. When a service starts failing repeatedly, the circuit breaker trips and temporarily stops making calls straight. Instead of having a broken service and causing a bigger failure, the system backs off and checks in periodically to see if the service is healthy again. This is how you avoid cascading outages. And the next one is bulkhead pattern. So this is named after ship design. Ships have compartments to contain flooding if one area is breached, right? So the same idea applies here. If one part of your system is under stress, you isolate its resources, CPU, memory, and threads, so it can't bring down everything else with it. And the next one is retry pattern. Sometimes failures are just bad luck, a blip in the network, a temporary database hiccup. In these cases, automatically retrying the request with some delay can resolve the issue without any user impact. And the last one would be fallback pattern. So these are degraded but functional responses that kick in when the real service isn't available. Maybe it's cache data or a simplified calculation, even a friendly message saying, hey, we are having some issues, we'll be right back. Fallback keeps the user experience smooth, even during failures. No, now let's try to see the API styles for the real world. So let's zoom in on how these services actually talk to each other and to the outside world. So let's look at REST. Of course, it's been around for a while and for good reason. REST is simple, widely understood, and works great for CRUD operations. It leverages standard HTTP verbs get, post, put, delete, and it's super compatible with browsers, mobile apps, you name it. But REST isn't always the best fit, especially when clients need precision in what they ask for. And that's where GraphQL shines. So with GraphQL, the client defines exactly what data it wants and gets just that. No more, no less. It solves the overfetching and underfetching problem, especially in complex UIs or mobile apps where bandwidth matters. On the other hand, gRPC uses HTTP2 and protocol buffers to enabling lightning fast communication between internal services. It supports bidirectional streaming and for strict contracts, making it perfect for service to service communication in large scale, high throughput systems. So, how do you choose between these things? You can use REST when you need simplicity, broad compatibility, and stateless communication. And you can use GraphQL when your clients need flexibility and you want to avoid bloated payloads. And we can use gRPC when you need raw speed, low latency, and strict type enforcement, especially for internal microservices. And here's the twist. You don't have to pick one. Many modern systems mix and match. REST for public APIs, GraphQL for front-end agility, and gRPC behind the scenes for speed. Now, let's look at the API versioning strategies, meaning like no broken clients. So you have built a beautiful API. It's like clients are using it, businesses blow me. Now comes the hard part. How do you change it without breaking everything? That's where API versioning comes in. It's not just about like supporting the old while rolling out the new. It's about doing it with clarity, stability, and trust. Let's walk through the major approaches. First up, URI path versioning. This one's simple and visible. You version right in the URL like slash API slash v1 slash products. It's easy to understand and route, but the downside is clutter. You'll end up with multiple endpoints for the same resource. Then there's query parameter versioning. You keep the base URI clean and pass the version products version is equals to 2. So this means this of course this approach is then neat and flexible and it works well when you want to switch versions without like rewriting paths like what we have seen previously URI path versioning. And the next one is header versioning. So you keep your URI completely version agnostic and specify the version in a HTTP header, accept version of v1, v2, etc. It's super clean for developers, but it does add a little complexity to testing and debugging, since versioning is now hidden in the headers. And finally, the most elegant but complex one is the content negotiation. So here, if your client asks for a specific version using the accept header with a custom media type. This one's incredibly powerful and aligns well with HTTP standards, but it also requires more sophisticated client handling. So which one's best? That depends on your use case. If visibility and ease of use matter most, go with URI or query para. If your consumers are more advanced or internal, headers and content negotiation offer cleaner long-term scalability. But here's the golden rule. Version early, version often, and never break your clients without warning. Versioning isn't a workaround, it's a commitment to backwards compatibility and smooth evolution. Moving on to the next slide. So here comes the documentation part for the APIs. So let's be honest, no one loves writing documentation, but when you do it right, it becomes your secret weapon. So start with the foundation. Pick OpenAPI or Swagger. These are mission-readable specs that define your API contract. And they unlock a whole ecosystem of auto-generated documentation, testing tools, mock servers, and even SDKs. It's like writing your API once and getting 5 things for free. Next, don't just describe parameters, show real examples. Give developers sample requests and responses in multiple languages. Bonus points for including edge cases and common mistakes. The faster someone can copy, paste, and see success, the better their experience is. Error documentation is also huge. Don't make people guess why something failed. Explain each error clearly, include the status code, a meaningful message, and this is key, what they can do to fix it. And don't forget change logs. Versioning isn't enough if no one knows what changed. Keep a clear, chronological list of updates, deprecations, and new features. And let's shield your system. Let's discuss about API security. So your API is the front door of your system. And if it's not logged down properly, you're basically inviting bad actors in. So let's start with basics, transport security. Every API call should be encrypted, no exceptions. That means HTTPS with TLS 1.2 or higher, plus things like HSTS headers and secure cookie attributes. It's a bare minimum for protecting data in motion and guarding against man-in-the-middle attacks. Next, we move into the authentication and authorization part. So, in this context, don't try to reinvent the wheel here. Use proven standards like OAuth 2.0 and OpenID Connect for secure delegated access. Once a user or system is authenticated, use JSON Web Tokens or JWT to pass identity claims securely. Just make sure to validate those tokens with signatures and expiration checks. And let's not forget role based access control. Not every user should be able to access every endpoint, right? Define roles, assign permissions, and enforce those tools by the API gateway. That's where security scales. Another must have is input validation. Validate all incoming data at the edge, types, formats, blends, and ranges. Sanitization prevents injection attacks and malformed payloads and all kinds of unwanted surprises. And this isn't just for user input, it applies to service calls also. Finally, implement rate limiting and throttling. You don't want a misbehaving client or worse, a botnet hammering your APIs until your infrastructure crashes, right? I have seen a lot of examples like that previously. So try to set some sort of like thresholds based on user rules, IPs, or authentication scopes, and always return those friendly rate limit headers so clients know when to back off. And next slide. Tuning for performance. All right. And now we have got our microservices built, our API secured, and now let's try to make them fast. Because let's face it, performance isn't just a technical metric anymore, right? It's a user experience metric, and users don't wait. So one of the strategy that we can use to improve performance is caching, of course. So we use HTTP caching headers like etag and cache control to prevent unnecessary requests. For even more speed, offload frequently requested data to something like Redis. Caching isn't just about speed, it's about offloading pressure from your core services. Pagination and filtering. So never return thousands of records at once. No one wants that. And your API can't handle it. So instead use cursor-based pagination for performance and stability. So let users filter down to what they just need. It's faster for them and cheaper for you. And also always zip your responses. It's a tiny change that can save huge bandwidth and speed up mobile experiences dramatically. Connection pooling. So every time you open a new database or HTTP connection, there's overhead, right? Pools let you reuse connections, cutting latency and improving throughput. Your services stay fast even at a node. And the last one is asynchronous processing. So not everything needs to happen in request response cycle, right? Push long running or resource heavy tasks into background jobs. Use queues, let your API return quickly, and handle heavy lifting behind the scenes. So, what are we getting from it? How can we make use of microservices and what are the next steps? So, we have covered a lot, right? And let's try to bring it all together with some key takeaways and roadmaps for what to do next. First, microservices are your agility engine. So instead of one team stepping onto each other's toes, you have got small focused teams shipping independently and confidently. So now what can you do with all this? You can start small, pick one service that's a good candidate to be carved out, design it intentionally around a business domain and build it with autonomy in mind, and then standardize your APIs, define your naming, versioning, and error handling strategy. It's one of those things that's easy to overlook but critical when you start to scale. And automate everything you can. Testing, deployment, monitoring. Automation isn't just about speed, it's about consistency and peace of mind, of course. And then prioritize security and observability from day one. You don't want to bolt those on later, you want them to baked into your architecture. And finally, stay it. You don't need to have it all figured out, just take the next step. Every cycle gets you closer to a system that's not just working, but working with you. Because at the end of the day, this isn't just a tech strategy, it's a mindset shift, one that empowers your teams to build faster and smarter. Thanks for being here. Let's go build what's next.